You're listening to Two Beers Until Phronesis, a podcast where we discuss the ideas of philosophy, ethics, religion, history, and culture. Alongside regular guests and friends, we discuss some of life's big questions over a few beers. Enjoy.
Fucking hell.
Open my almanac.
Straight fire in the booth. Here we go.
Right, so we're going to try something a little bit different today. I'm just going to basically let you two lay all this quantum mechanics stuff on me. I have basically no background in any kind of science, so I'm basically just going to be an audience surrogate for this whole thing.
Your job is to ask questions when it stops making any sense and it starts getting a bit too much. But essentially, we're going to go through quantum mechanics, start with the historical perspective, so start with why this sort of even exists in the first place, all that sort of thing. I'm going to start broadly with describing what quantum mechanics is as a field of science. Mm-hmm. So for a start, it is essentially just the study of the smallest things. Quantum is actually Latin for how much. Essentially, it was quantum equals what is the smallest possible amount. And mechanics, just how does it work? What are the equations that govern it? How does it describe our universe? It's one of the most successful physical theories ever tested. Essentially, it makes up everything. So just because something is big doesn't mean it isn't, in some sense, governed by quantum mechanics, because everything is made up of the smallest things. Some of the most obviously well-known applications are things like nuclear power plants, atomic clocks, digital cameras, transistors.
Sure.
Yeah, I sort of wanted to sort of start with the history and all that sort of thing. And also, we got Joe with us as well, who you have actually done some decent amount of studying in maths and things like this, and you have done some modules on quantum mechanics a while ago.
Yeah, I might be able to chip in with some of the maths bits if we get into that.
Nice.
Yeah, we'll see how technical we get.
I mean, I'd pretty much just be happy if, at the very least, from this podcast, we can just situate it within a context and then kind of get the rough sense of it across to people listening. But anything beyond that, excellent.
Yeah, so the goal is to try the best we can not to get too far into the maths, but it is worth remembering that ultimately these descriptions of our reality do not really correspond to the way we see the world on our level in what would be called the classical world, or the world of objects and things and all this sort of thing. A lot of that becomes way more abstract when you go down to these levels, and so many of the common ways in which we think about the world start to really kind of break down. And so the way which you have to describe them with analogies aren't necessarily that accurate, but it's the best you can do to try and get an intuition for what the maths is saying. And sort of later on, we'll realize that what's really weird about quantum mechanics is, even though we have all of these equations that are governing what's going on, how we interpret what those mean about our physical reality is very much an unsettled debate that is still going on now and is extremely interesting. And that's hopefully what we're going to get to. You may have heard of things like cats being both dead and alive, infinite universes branching away, all these sorts of things. That's when you start to think about interpretations and the philosophy and the ontological description. What does it mean? But I thought I'd start by going all the way back to 1687.
All the way back to 1687.
All the way back. When Newton published Principia Mathematica.
Is it a great read?
No, he wrote a whole book on why 1 + 1 = 2. Right. Well, that was the precursor to Principia Mathematica. Right. I haven't actually read it.
Yeah. So this was obviously famous Isaac Newton. This book totally it was a whole paradigm shift in the foundations of what we understood about the physical world. It was more or less unchanged for about 200 years. And it was essentially a description. This is something you still do in physics classes. It's F equals ma. The world is objects, things. Aristotle before him would describe the world in terms of things needed an agency to move. You needed to give something.
That's trying to give an explanation to what you were saying about the classical world. Aristotle's paradigm of science is literally just looking at, okay, what does it look like is happening? I'll describe that. And that's as far as the model goes. I guess this is just like the model is so abstracted. So I guess that's why people find it relatively hard to...
Yeah, it's more that... So Aristotle thought that objects needed an agency to move.
Because, so like the way he would use it is like, so gravity, a feather doesn't love the earth as much as a rock. So he would describe it, because that is pretty much what we're seeing. It's just a flowery way of explaining it. But that is pretty much, as far as the eye can tell, what is happening. It seems kind of stupid to us, but
like you said, with a feather in a rock. Obviously, in this example, what's interesting is then later we realized, and one of the famous sort of Newtonian paradigm things was that the forces that govern both that feather and that rock end up meaning that in a vacuum they do hit the ground at the same time. So
so it has nothing to do with the feather and the rock.
So the Earth loves them both equally. But, but it is to do with different forces. And what's interesting is that whole paradigm shift came from, say, you have a glass on the table and it requires some agency. It needs to want to move, whether you push it or something like that. But normally things just want to stay where they are. And the paradigm shift with Newtonian physics was this whole idea that, no, if you push something and there's no force to stop it, it's just going to keep moving. One of the main interesting things about Newton is everything became sort of objects and tiny little things that would move about, and they obeyed these simple mechanical laws. This is what we call classical mechanics, and still we use a lot of this idea of what's called classical mechanics to describe the macroscopic world. When he tried to apply it to light, a lot of what he thought was, well, everything seems to be objects, so light, it seems to obey the same laws. It goes from one place to another and seems to obey these simple equations. So light must be made up of these tiny little dots and bits and pieces. Yeah. But at the time, this was competing with the idea that light was a wave. And Descartes before him was actually one of the first people to think that light was made up of little packets. But because Newton was so influential, and Principia Mathematica, however you want to pronounce it, was published, that people just didn't question it. Went, okay, well, light must be objects. This guy knows what he's talking about. He invented calculus and all this sort of thing. He knows what he's talking about. And so it kind of wasn't questioned until much later, when we had, in about 1801, which is, maybe 20 years later, Thomas Young's double slit, and he essentially showed that light behaves like a wave. So this was weird because obviously up to this point they thought, well, okay, it's just like little objects flying at things, right?
Yeah.
And then what happens is if you put two slits in a thing, in a wall or whatever, and you chuck light through it, what you'd expect to see in a Newtonian universe is you get
like a beam.
Yeah, so if you chuck a load of light through a thing, it should project onto the outside wall and it should just look like two slits that it's gone through, right? Because it goes through one side and goes through the other as well. So they're all sort of all these little bits of light are just going through. But what's interesting is you can show that light, at least when it is in a what's called a coherent form, we'll go into that later. What was weird about these experiments is that was not the pattern that you see. When light goes through these two slits, you see what's called an interference pattern on the other side, on where it is projected onto. And what that basically means is that light isn't just like going through single-mindedly and sort of hitting the other side of the wall. At least it isn't always. But it's showing a sort of pattern of like multiple strips of light that are sort of like, much stronger in the middle and then sort of like get weaker and weaker and weaker until they fade away. And essentially, if you can imagine like a swimming pool or something like this, and let's say you have a barrier in the middle of the swimming pool. In this barrier, you've got two slits again. Now, the water's perfectly still, let's imagine, but you're on one side of the barrier and you like slap the water or something like that, right? So you're creating a load of waves.
Yeah.
Now, what happens is when those waves hit those little slits, right? What are you going to see on the other side? You're going to see little sort of like shock waves propagating out of these two gaps into the still water, right? What happens when those two sort of like shock waves start to touch each other you imagine two circles just sort of like
going outwards.
Yeah, going outwards. And what you see is when they start to interfere, like that's the technical word, they start to interfere with each other, you get the peaks of those waves, so the bits where the water's going upwards, add together. So like where the two slits are sort of coming together, you'll get larger peaks, larger waves, and where the two sort of troughs, sort of meet up, you'll get you get less water essentially. So if you can imagine how that would propagate onto the back end of the swimming pool, you're not going to see a simple pattern of just like two slits coming through. What you're going to see is this pattern of like bits where there was like extra water, where the peaks were higher because of the interference, as well as like extra troughs as well.
Yeah.
And so this is what an interference pattern is. It's where you have a wave or something that is like a wave. In this case, it was a swimming pool, but for these guys, this was light. So in this case, they were thinking about light in terms of like, why is it creating this pattern? It's just like an interference pattern, like that you see with waves. So that's what it must be, right? So light must propagate like a wave. So it's just a thing that causes like almost like this vibration, and this vibration travels out, and we can see that by doing this double slit experiment. And then Maxwell came along quite a while later, actually. It was just, quite a long time later, and totally wrote down all the maths describing these waves.
So what kind of date is this?
So this is around 1850. Now we'll be getting to James Maxwell. And essentially, he just formalized this into equations that worked for these kinds of light. And by this point, this is getting pretty complicated because we've already figured out that light is it's what's called electromagnetic radiation, which basically means it's related to electricity and it's related to magnets. But essentially, it was quite a complicated description that described how these waves oscillate through the air, and we had all the maths to sort of write down how these were behaving. So we could describe why we get this interference pattern on the back wall. We could describe how light propagates and interferes with itself and all this sorts of stuff. And so at this point, people were just like, okay, well, light's a wave. This makes sense, right? It's not little objects like Newton thought. It is this thing that sort of interferes itself. It's a pattern. It's continuous. Great. Okay, cool. Sorted.
I'm guessing there's going to be a but.
Yes. I mean, this was confirmed in 1887. There was by Heinrich Hertz. And I bet you can't guess where the term Hertz for frequency and things like came from. It's this guy for proving that the Maxwell equations were not just a description, but they worked in experimental situations, that these equations perfectly described what was going on. And by this point, so we're talking right at the end of the 19th century, right? Stuff like light bulbs were all the rage. People were loving their light and their electricity and things like this. It's all great, after Newton basically wrote the rules for the Industrial Revolution hundreds of years ago. And so people wanted to figure out, okay, what's the best way we can make light bulbs? How efficient can we make it? We want as much proper light as we can get out of this light bulb with as little energy as possible.
Those were the days before energy-saving light bulbs.
Yeah, we've all regressed. And right at the turn of the 20th century, we have the guy who's considered basically the founder of quantum mechanics. Sort of starts to come into the picture. But before that, we'll sort of talk about how light bulbs were thought to work. Well, how the light propagating out of light bulbs was thought to work. And this was described by this graph that was called like the Rayleigh-Jeans law. They were going off of Maxwell's equations pretty much entirely, and they were just going, well, okay, well, what we should see is that when you put a load of heat into something, this actually worked for like really low heat. So for like infrared and things like this is totally fine. Once you start to get really hot, what the experiments showed is that you don't end up having tons of ultraviolet radiation. What you end up having is it glows a certain temperature, right? So you might notice with stars, right? They glow a certain color depending on their size.
Yeah.
The reason why that is because the temperature is related to the wavelength of light that is predominantly being emitted. And so this was weird because that's what the world seemed to look like, right? We had different heat and different things like this corresponded to different light. When it wasn't red hot, let's say, and it would just be like, if you're sort of hot like we are, that's just infrared radiation, right? It's the same thing, but it's in the infrared spectrum, so we can't see it unless we have infrared goggles. But you keep moving up, and then things start to go into the visible spectrum, so we can actually see the heat, and then it goes beyond us, and it goes into UV, ultraviolet. We've got X-rays and gamma rays. Essentially, the original predictions were that, well, surely if you heat something up, it should all just be in these infinitesimally small ultraviolet radiation. Because as soon as you get some energy into these atoms and into these systems, they should just instantly be emitting this really high frequency, tiny amount of light that just carries away all the energy. Obviously, this is not what we see. And so there was this weird thing where experiment and reality was not conforming with what the equations were telling us about what light was. And so this is where Max Planck came along. And essentially, he was trying to figure out, okay, how can we get like the most efficient version of a light bulb? How can we make most of the energy translate into visible light? This is what we want. We want a particular part of the electromagnetic spectrum, right? We want as much energy as possible to be in this part. We don't want it to be all like infrared, which we can't see. We don't want it to be all like ultra high sunburn. Mm-hmm. You don't want to get a tan from a light bulb. What's the best way to do that? And essentially, Max Planck was like, well, why the hell does it look like, using what we know, everything should just be ultraviolet? It should just be these ultra high frequency stuff as soon as you get any energy into the system. This was all based around things called black bodies. If you want to go Google that, we're not going to go into detail of what those mean, but they were essentially a theoretical way of talking about the frequency of light that was being emitted. It was just like this theoretical perfect way to describe the maths that was going on. And Max Planck basically went, okay, well, I can't figure this out. I don't understand why these equations just don't work. Why is, if light's this wave, why isn't why doesn't our predictions for how the light will be emitted, the frequencies that will be emitted, not conforming? And he essentially just went, in what he called a last act of desperation, he just introduced a number into the equation. So he went, it was basically making it so it could only oscillate within a certain harmonic, which is to say that he introduced something that made the frequency have to be a multiple of a certain number. So that is to say that the frequency couldn't just be any arbitrary frequencies. You couldn't have like an infinitely small frequency, because that was the problem. It's like, well, surely if you look at the prediction, all the energy should just go off towards like infinitely small frequencies. But you can't. But he basically introduced this thing and goes, well, what if we quantize it? What if we put this little term in there?
Yeah.
And hey, he adjusted it a bit, whatever, got it, like fiddled with it, just try to make it work. And suddenly he got a curve that perfectly explained how the different levels of different frequencies of light were being emitted from these black bodies, or essentially extrapolate that to the real world, how light bulbs and things were emitting certain wavelengths of light, given the amount of heat. But this was like, what the hell? I mean, light's waves, right? I've talked about the swimming pool analogy. Like that's what light does, right? It does these patterns. It interferes with itself. It's continuous. And yet here comes this weird constant. He didn't know what to think of it. And I mean, Rayleigh and Jeans, who were like the two guys who came up with these original laws, actually thought this was an embarrassment. They were like, this is disgraceful. This is awful. This is bollocks. This is because this is something we don't know about black bodies. It's something we don't know about light or something. We're missing something here. Why does this random constant actually work? And this was right at the turn of the century. This was 1900. And as some people who are into their science might know, 5 years later, Einstein published stuff like special relativity, stuff from Brownian. Like in 1 year, he basically totally changed the paradigm of science, as many people know. This wasn't general relativity yet; that came later. But this is something that he would go on to win a Nobel Prize for. And this was essentially, he took Planck's constant and made sense of it. He went, okay, what does this mean? This means that light is a particle again, in some sense, but it's also kind of a wave. So it's kind of a particle and a wave because, well, we have this constant that kind of quantifies it, and this is where the concept of a photon came from. And he would go on to, this is the only Nobel Prize Einstein actually won, was for discovering the photon. Really? Yeah, which is something that a lot of people don't realize. It's like general relativity, because that is more of a theoretical framework, didn't.
Yeah.
But this is what he won the Nobel Prize for.
In terms of is the photon something fundamentally new? Like, or is it building on previous kind of understandings of things? Or is it like just a total game changer?
So he related energy to the frequency of light. So times Planck's constant. So he took this idea and he went, well, what does this mean? What does it mean that frequencies can only exist as multiples of a particular number? That means that light must have particles. It must come in discrete packets. Essentially what he was saying was that energy cannot be passed on from a photon to, let's say, an electron. Electron is another fundamental particle that you get in atoms. You can't pass on energy in a continuous manner. It has to be done in these packets. And this was important because he made experiments like where you'd fire light at a metal plate, basically. And if the original wave-like thing was true, then what you should see is like as you increase the amplitude of the light, if you just chuck more and more light at a plate, you should see more and more electrons firing off this plate. You should see, because the photons will, well, at this point, not sure about photons yet, but this was sort of the idea is if it was a wave, the waves would interact with photons, they interact with electrons, and these electrons would get enough energy to be like, oh yeah, let's just bugger off now, guys, and they would fire off the plate, right? So that's what you would expect to see. But what was weird is you'd only see this dependent on the frequency of the light. You didn't see this if you just chucked more infrared light at a plate. So if you chucked lower frequency light at it, but loads of it, at no point are any electrons being fired. So they were like, well, that's interesting, because that can only be the case if it's individual photons that can carry a certain packet of energy, and once that packet of energy is high enough, aka the light is a high enough frequency, then it can interact with the electron in such a way that it increases the electron's energy enough that the electron can bugger off. And one way I sort of started to think about this, and I don't whether this is a useful analogy or not, is imagine that you've got a load of soft balls, right? So like spongy balls, and there's like a window in front of you, and you've decided you want to like try and break the window. So you've got a load of these soft, crappy balls, right? And you're just throwing them out the window. And it's like, they're not doing anything, because it's just like they're crappy soft balls, right? So, you know, you can throw as many, you can get like a whole bucket of them, just start throwing them at the window, just keep as many as you want. The window's not going to break. It's not even going to crack. They're just spongy, crappy balls. They just bounce off.
Yeah.
There's just not enough there. Whereas if you get like an 8 ball or like a, you know, a pool ball or a snooker ball or whatever, and you throw it at the window, the same sort of like, you know, same amount you were throwing this ball, it's going to smash the window, go straight through, right?
Yeah.
The only, and this is the thing, it's like, if it was a wave, if you were using like a hose or a super soaker, the only thing that would make sure the window smash was the pressure of the water. So if you've just got enough water, even if it was like, you know, fairly low pressure water, you just have to get enough and it would like break through the window because the pressure. But this was one of the things. So this means that like, okay, well, individual things, if there's not enough energy in these packets, they cannot actually bring what was called energy levels, which we'll get to later. They cannot excite the electrons enough. And so this is, broadly speaking, the reason why the photon was discovered. It was like to do with energy levels, and it was to do with the fact that experimental evidence was not conforming with it. Planck sort of adjusted it, and then Einstein went, this means that there are these discrete packets of energy. And he related to an equation that if you want to go look up, you can, but it's really simple. It's just E equals HF, which is just the energy is equal to Planck's constant, which is this minimum value multiplied by the frequency. So it just means that this number, Planck's constant, has to be multiplied by the frequency, and it can't exist in a smaller amount or a non-multiple of that number. So yeah, I've done a lot of talking so far. We're almost at like the really meaty stuff of quantum mechanics. So we're getting through some of the history, and we're already realizing that there's this weird stuff going on where we're having these experiments where it's like, well, double split, it's like a wave, and then Einstein comes along and Planck, and they're just like, well, also it's a particle. It has to be sort of a particle because it has these particle-like properties. But we still see diffusion patterns. We still see these sorts of, so how do we explain those sorts of things?
Yeah, trying to get like a handle on how it all actually works in terms of, you know, so that the model matches up with functionally what's happening.
Yeah, exactly. Yeah. And this was what's so weird. It was this was the maths that was describing what was going on with light, but everyone did not like it at all. Like, you know, Einstein himself hated it. Like, they were all just like, well, this is totally shattering this nice, neat idea of something being one form and described by one set of equations and not being. It's sort of like, and this is where you might hear the term particle wave duality. This is where it was all birthed in 1905. And that was his Nobel Prize in 1921. He won the Nobel Prize for that. I should sort of start to introduce this guy called Niels Bohr. So this guy, we're sort of going up to about 1913 now. And Niels Bohr was another guy who's a massive player on the scene of quantum mechanics in its originalism. As we've already sort of established, like, this is where quantum mechanics really started with Planck and Einstein, and there's this particle as well to do with light and all this sort of thing. And Niels Bohr comes along and he goes, this should have implications about the atom and what the atom looks like and all that sort of thing. And up until this point, there was like a Kiwi scientist called Rutherford. And he had this model of the atom, which is kind of familiar. I mean, it's not quite like the one we use in textbooks, but it's pretty much there. It's, you know, it's electrons that are negatively charged and they're orbiting something, you know, it's like some positively charged nucleus, right? They thought that it was literally kind of like things, negatively charged things, actually orbiting a nucleus. And Bohr went, well, hang on a minute. So we got this new weird quantum mechanics stuff. So we can take this further. This was actually presented with Rutherford as well. So Niels Bohr actually studied under Rutherford. So this was kind of like him taking that model and going on and using Planck's constant to basically show that the electrons, as they're orbiting this atom, so this is the Rutherford model, you got this negatively charged thing, it's just whooping around the nucleus, right? It's just, but what should happen, right, is that if the light can just get rid of the energy in any amount, any tiny little amount, what you should see is this electron should just be giving away this energy in tiny amounts, take away energy from that orbital rotation. Let's imagine you try to slow it down. It should just immediately just like decay into the nucleus of the atom, and all the atoms should just suddenly completely blow up. Of course, this is not what we see. And so Niels Bohr came along and explained this using Planck's constant, and using the idea that there was a minimum packet of energy to say that electrons can only be in what are called certain energy states. So if an electron's in a certain state, there has to be a certain amount of a threshold of energy you need to give it or take away from it in order for its orbit to change in the atom. We're still talking about it in terms of orbits. Of course, this picture kind of changes later on, but for now, that's more or less what textbooks now still use. In if you're doing physics, you're going to see Niels Bohr's picture of the atom, which
I was going to say that's pretty much what we would have seen.
And I mean, even I think you probably do it at GCSE energy levels. I can't remember if it's GCSE or A level at this point, but you basically have atoms, electrons flying around, and we talk about the different energy levels for these electrons to be at. And this is how a lot of chemistry happens, right? It's just
I never paid attention in GCSEs.
Yeah.
I think you do like the Rutherford model and the plum pudding model, whatever they called it. I think you only really get into energy levels at a technical context, probably A level.
Right.
Like E equals HF that you mentioned earlier, that was all A level type stuff.
Yeah, you mentioned the plum pudding model. This was even before Rutherford. Essentially, they just thought that it
was all just a gooey mess.
It was all just a gooey mess of a positively charged blob, essentially, that had, let's call them like raisins that were negatively charged, all sort of stuck into this blob. That's why it's kind of like a plum pudding model. It was all just like this blech, that was kind of like, and then later on Rutherford described it as orbits, and then Niels Bohr comes along and goes, well, there's also these energy level things, and that's the reason why these atoms aren't just instantly exploding, because the energy can't be carried away from these electrons the way that we thought they might have been able to. So yeah, that was Niels Bohr coming onto the scene. As we know, he's a pretty big player, so we'll come back to him in a minute. Obviously, then World War One happens, and not a lot really happens during World War One. I think a lot of the scientists are kind of all
in physics.
Yeah,
it's interesting because obviously, like, there's the whole phrase. What is it? The mother of all invention is necessity. Is that? I don't know if
that sounds right. Yeah,
I don't know if that's the actual phrase.
Yeah,
he was saying obviously about trying to create the light bulb, and that obviously drove a lot of
trying to figure out how to make a light bulb as efficiently as possible.
Did World War One not like spur any invention in this field, or were they
not
just
really? I mean, for the most part, if anything, it probably with quantum mechanics and pure theoretical physics, because we're talking about theoretical physics for the most part. Obviously, there's experimental verification that will occur later on, and that's where Nobel Prizes and things get won. But for the most part, these guys were writing down these descriptions and equations, predicting from sort of first principles or from the maths, or looking at previous experiments and trying to describe and trying to explain why they work the way they do. And later on, their equations will be experimentally verified. But during the war, I mean,
I guess the international kind of stuff stops.
And there's a lot of
collaboration.
At least with the history of quantum mechanics, I'm not a historian when it comes to this stuff, but there is definitely like a little bit of a pause, at least when it comes to, and maybe if you really zoom in to look at like what was the details are going on, I'm sure there were
that's certainly understandable in World War One. I would be surprised if nothing happened in World War Two.
Yeah, and we'll get to what happened there, but so we're going to zip forward all the way to 1924 now. So this is about 6 years after the war. And
I remember it well.
Yeah, and obviously there's probably been loads of stuff going on in the background, but for the sake of getting to the next bit, we're going to introduce another character. And I've heard lots of different pronunciations of his name. I'm going to call him De Broglie. I think that's the correct way to pronounce it because he's French, but I'm not going to. So I'm not going to say it like that because I think that's the correct way to say it. But people say either De Broglie or De Broglie, depending on whether.
Can we call him De Broglie? That makes him sound like an absolute chad.
We're going to call him.
I did call him
De
Broccoli for a bit, so I just couldn't fucking say his name.
He's De Broccoli from now on.
De Broccoli. So the Broccoli man. I can't do that. So this guy is weirdly, like, when I was looking up a lot of different the histories and people explaining it, he's often left out in a lot of the histories, which is interesting to me, or at least the briefer ones. And he was a really important player in quantum mechanics. And in 1924, he predicted matter waves. So essentially, what he was doing was going, well, okay, light's a wave. Why aren't electrons and things like that also a wave? So this is like a whoa sort of moment. And this was a guy who worked in like radio broadcasting and things like that. So he had a very good understanding of Maxwell's equations of light and waves and things like that. And he just sort of extrapolated it and predicted that all matter had some kind of wave-like properties, even if they were we have these wave and particle-like things going on, and oh god, what's happening? But if photon can be sort of like a wave and a particle as well, why can't an electron or a proton or whatever arbitrary particle you want to pick? And this was much later on just demonstrated in 1927, this by experiments confirming that electrons also exhibited wave-like properties. Much sort of harder experiments to prove with light, but that was a 1929 Nobel Prize for him. So as you can tell, like, a lot of these people are all Nobel Prize winners, because this is an absolute honeypot of Nobel Prizes, is quantum mechanics. You've got so many around these couple of decades. You've got so many people winning Nobel Prizes for these things. He was also the guy who originated what we'll come back to later, a thing called pilot wave theory. But we're not going to go on to that yet. Sort of going back to the mid-1920s, I'm going to introduce a guy called Heisenberg. And this guy is another major player in quantum mechanics, as all these guys are. And he was trying to figure out how to describe what we were kind of finding out about particles and waves and all these sorts of things. Like, how do we describe what is going on? What are the mechanics of these tiny, smallest things that we can experimentally look at? And he was formulating something called matrix mechanics, which, I haven't even looked at it, so I'm not even going to try and go there, because obviously this was all kind of like developed on later on. But he was trying to think about the maths that was going to describe these weird quantum properties and the way things were working. And at this point, these are mathematicians that are pulling all the tricks out of the book that maths had to offer at this point and inventing a lot of maths just to help describe what was going on. This is how difficult this stuff was, how weird these properties that things had were. And also a guy called Paul Dirac, who was a sort of French, but also sort of grew up in Bristol guy who was very, very, very shy, and essentially kicked off the entire field of quantum electrodynamics, which sounds scary, but it's basically the smallest electro. So we're talking about electromagnetic spectrum, light and things like that, and dynamics, how it behaves. So
it's probably what we describe as a savant today. It probably wasn't a diagnosis then, but he would have been on the Asperger scale, sort of at the top, probably.
Yeah, definitely.
So he was very, very socially awkward, didn't fit in at all with people, didn't really work with people, but an extraordinary mind nonetheless. And he, as Nye said, he spurned many, many fields of quantum theory. Yeah,
and unfortunately, just poorly remembered, like compared to some of the other main players. Understandably, Einstein, did some pretty cool stuff, did some pretty amazing stuff, but definitely underappreciated.
We'll probably get into it a little bit later, but as I was saying to you earlier, he actually invented a whole new notation to try and describe some of the stuff called Dirac notation, which you may or may not have heard of, which is just essentially when things get very, very hard to write out, he developed quite a compact way to just put vectors in of descriptions of quantized properties of particles.
Right. So things like spin or whatever, which we'll maybe get to later and describe. Obviously, you have different states of these fundamental properties that they can exist in. And they didn't really have a way to write, the easiest way to write it down was to literally have an arrow pointing in the direction of what the property of this fundamental thing you were describing. So again, we're talking all these sort of different bits of notation and mathematics totally being, renovated in order to accommodate all these crazy experiments and the things that we were figuring out at the time. So we have nothing to do with this. not even a close. And he's also the guy we mentioned spin. We might get to that later. It's another weird quantum property that only really exists on like the quantum level. Obviously, it has effects that propagate outwards, but he was one of the guys who really started to describe things like that. I have an actually interesting, just to get you an idea of the characters of Dirac and Heisenberg. So I have this quote that I pulled from it was like a book that I looked at the Guardian article that was reviewing this book and just took some quotes out of it basically. But I'm just going to read off of this. So in August of 1929, two of the founding fathers of quantum mechanics, Werner Heisenberg and Paul Dirac, were sailing on a ship to a conference in Japan. Both still in their 20s, unmarried, they made an odd couple. Heisenberg was a hedonist who constantly flirted and danced with women on the ship, while Dirac, an Edwardian geek, as Graham Farmello puts it, suffered agonies if forced into any kind of socializing or small talk. So, why do you dance? Dirac asked his companion, Heisenberg. When there are nice girls, it's a pleasure, Heisenberg replied. Dirac pondered this notion, then blurted out, but Heisenberg, how do you know beforehand that the girls are nice? It's just like, gives you a total idea of his character and just like totally, like you said, very likely to compared to these days standards on the spectrum, all that sort of thing, but an absolute genius. Heisenberg almost being the total opposite, who was one of the people who helped work on a lot of this maths. And so together they more or less came up with a lot of these notations and a lot of ways to figure this stuff out. And so I've sort of missed out a lot of the very fundamental bits of equations and whatever that are sort of being introduced to describe all this weirdness that's sort of going on with particles and waves. All this weird math was coming up. And then a guy called Erwin Schrödinger basically came onto the scene and showed an equivalence between a lot of these like weird math systems that were sprouting up, and he sort of generalized them, if you like, which in maths basically you're putting it into a more abstract form that's a broader description of what's going on, or a more fundamental description of the same sort of thing. And he generalized all this matrix mechanics stuff and all this like crazy notation into what is going to be probably the most fundamental thing we're going to talk about in quantum mechanics, which is the Schrödinger equation. The Schrödinger equation is essentially a complete description of the evolution of a quantum system. So what I mean by that is that if you take a quantum object or quantum thing and you want to know how it's going to evolve, so how it's going to change over time, the Schrödinger equation describes that. And it essentially takes this other very, very important concept, which we'll try to describe a little bit. Joe can help me out on this one, which is called the wave function. And we've already talked about waves and interference patterns and things like this. We've got a little bit of an idea of like what it means to be a wave-like property. And essentially, the wave function is a mathematical description of these waves, of the wave-like properties of quantum particles. And the Schrödinger equation essentially takes this wave function and it describes how the wave function evolves over time, how it changes over time, given a quantum system. So there's a lot of jargon being thrown around. I understand. But these are really, really, really important ideas.
It's like
Ant
Man and the Wasp, mate.
Yeah, in those films where they just like throw away like the wave quantum chrono wave function of
the quantum van, the quantum fucking exhaust pipe, quantum everything.
Yeah, so that's an interesting thought actually, because if you think about it, if Ant Man shrunk and all his atoms retained the same size, surely that means also Planck's constant would also get smaller to accommodate that. In which case he would just die instantly because the heat would be immediately evaporated.
That's what the suit is for.
That's what the suit's for.
Those producers really thought of everything.
Yeah.
Oh, they actually thought of it.
Yeah,
I
think they talk about Planck's constant at once or twice.
Yeah.
And I think that is the whole point of the suit.
Right.
This is why the guy who made it is a genius, because he's made a suit that will stop that from happening.
So it will retain all electromagnetic radiation, all light and ultraviolet rays that would emit, like all these things that would totally disrupt everything.
Apparently
so. Immediately, because I will imagine. I mean, this is such a difficult.
I'm pretty sure he takes the helmet off though and still shrinks. So just
because you need to see his face.
Nonsense, because he's Paul Rudd. He needs to get the money and contractually obliged to show his face.
Yeah, well, I'm sure there is definitely some people on the internet who have definitely gone into how Planck's constant would work in that case.
Is it you, Nye? Behind like 50 accounts.
You've got me thinking about it. Oh, God. Yeah, and so we've just introduced really important concepts. So the Schrödinger equation and the wave function that it is describing, everything you need to know about how a quantum system works. Obviously, there's other sort of things going on, but for the most part, if you want to know something about it, this is your equation. And we won't. Yeah, I don't think we'll be able to go into like breaking down all the parts of it. I'm sure, but like maybe in like another episode where we talk about, maybe when we get into interpretations, we might start talking about like different parts of the equation or like things like that. But for now, this is more or less where we still are to today. And this was the mid 1920s. So this that Schrödinger wrote this down. The Schrödinger equation explains how a quantum system evolves. Is weird because again we've got this weird particle wave-like thing, but the thing is it's neither. So what ends up happening in experiments, and I'll this is the first time I'm going to start invoking physical interpretations of what's going on, but it's the only way you can start to really explain it without digging into the maths, is that as the wave function evolves, so you can imagine this sort of wave evolving, and the Schrödinger equation tells you how that wave function evolves. You get all these diffusion patterns, you get all these things, but the minute you measure what's actually going on, to try and find out where the particles are going, it's a particle and a wave, right? So so if it's moving like a wave and you get diffusion patterns and you get wave-like things, well, let's stick a detector in there. Let's just try find out, okay, where are the particles then? If we're seeing wave-like stuff, why are particles the things that we interact with? Why are those the things interacting? Let's try find out where the particles are. So let's go back to the double slit experiment, right? And we're firing light through these two slits. In this case, much later on, they started to be able to get the technology. This is in the probably 60s, 70s now, that they start to be able to fire individual photons. We're like talking little individual particles through these at these slits. And then what they do is there's a detector at the back and it just finds out, okay, well, where do the particles hit the screen?
Where they ended up,
Yeah, so we'll be able to see what a pattern emerge. So let's fire a load of photons through these two slits, right? So what would you imagine if it's a particle? All of the photons, in this case, would just line up into two neat lines because they would either go through one slit or they go through the other slit. But what you see, if you just fire these photons through the two slits, is you see that weird interference pattern again. That thing that looks like waves have just gone through the slits. But you've been firing individual photons. How do they know to make a wave like that? If you're firing individual ones, surely that means that they're going through one slit or the other. Like, what's going on here? This is mental, right? If we evolve the way the photons are going according to the Schrödinger equation, if you evolve the wave function according to the Schrödinger equation, sure, we should see an interference pattern, but where are the particles coming from? Why are there particles? Why is it when we see the thing, there's like an individual thing? So, okay, let's try to find out where the particles went. Let's try to find out which slit they went through, okay? So let's put a detector on each slit, and let's see if we can figure out, okay, let's fire another load of photons at it, and see which detector it hits before it hits the back.
Okay.
So firing loads of photons at it. Oh, cool, that photon went through B. Oh, cool, that photon went through. Oh, great, yeah, that seems to be about 50%, whatever. But hang on a minute. The pattern at the back is now just two lines again. So hang on. The minute we try to find out where the photon went through the two slits, it's no longer a wave. But then we take away the detectors. Oh, it's a wave pattern. What? How has that happened? And how do the photons know to make a wave-like pattern over time? If you fire individual ones, eventually it'll look like a wave pattern, even though they're just like individual dots that are being drawn. How does it know? And so what the Schrödinger equation says is that, well, we've got this wave-like thing that's evolving, and what the predominant interpretation was at the time is that as soon as you interact with the system in some sense, as soon as you observe the system or try to look at the system, it collapses. The wave function collapses into one particular place.
I'm guessing this is where the whole Schrödinger's cat comes from.
Right. So I'm wondering if we should, should we do Schrödinger's cat?
Yeah, so I guess to explain to an extent about the collapsing thing. So one way to think of the wave function, which is how I was kind of taught, albeit in very simple terms. So when I looked at it from a maths context, we kept the physics to sort of a minimum, and it was basically just the quantum system that you referenced earlier, Nye, is basically just a particle is somewhere in this region of space, but we don't know where. And what the wave function does is doesn't describe where it is, but it describes a probability density of where it is. So it might be, we can't say the particle is here, but we can say it's within this subregion with a probability of X%, whatever, it doesn't really matter.
Yeah.
So you can then build up what's called a probability density function, which is just a mathematical thing to describe where you are more likely to find the particle in this region of space at any time. And then you set the Schrödinger equation off running. If it's a time-dependent one, you'll be able to see it, kind of the density function, move around the whole of the space through time and through space. So the Schrödinger equation's got a time and a space. I don't know if you mentioned that, but
yeah,
there's a time-dependent version, which is more complicated, where the particle is depends on the space and also what time in your system you're measuring at. And the time independent version is more simple, where you just ignore time and you look at where it is in the space. And the act of actually measuring where the particle is, so when you're saying earlier, Nye, about putting the detectors in, that was a measurement. Collapses the wave function just means that the probability density function changes.
It converges to one.
It converges to one. Yeah. So we now know that the probability that the particle was in this particular point in space with 100% probability and 0% everywhere else. And that is effectively the effect of measuring it.
Yeah.
Collapses the wave function, i.e. changes that density function to this is definitely at this point.
Yeah, absolutely. And obviously this is counterintuitive. You're not alone. this is obviously we're already getting into like the very, very weird stuff. So this is heavy things to start thinking about. And obviously I have no idea like how...
If I understood that correctly, so is it kind of like analysis by reduction? Like finding where it isn't to find out where it is?
What Joe described there with the probability thing. So there was a guy called Max Born. So and around the sort of same time, mid-20s, he was able to describe where you'd likely to find the photon based on this wave. And it's where you square the wave function so you get a probability. And that's all you sort of need to know for now. You just essentially square it, and then that gives you a probability distribution. And so people like Heisenberg, so Heisenberg was very much an advocate of the idea that what it meant to be a photon was to exist as a probability space until it became an actual thing, until it was measured and actually became in one of those potential places it could be. And that until that point, it is this probability density. Now, Niels Bohr, who I mentioned earlier, some guy who I really was figuring out, he was who's sort of like one of the more sort of charismatic and influential people, who was sort of like the originator of what a lot of people consider to be the Copenhagen interpretation. So this is, I'm going to sort of go into that, but his idea was that it's a bad question to ask where the photon is. It's a bad question to ask what it means to be a photon before it's not a question you can ask. And there was all these, we'll get into complementarity and things like this later on, but it was based on other things that you can't measure one thing without losing information about another. So there was, again, this is why Copenhagen as an interpretation, when we talk about wave functions collapsing or what it means to be the wave function before it collapses, subtly different depending on which person's interpretation of Copenhagen it is. They all sort of have this idea of wave function collapsing. So the maths describes this evolution and it exists in this probability space, but you measure it and it's immediately in one place. It's not a wave that's everywhere at once. You never interact with a wave, and that's the point. It propagates like a wave. It propagates like this probability space. But then as soon as there's any interaction, there's a detection, you see one photon, you see one thing in that place. And this is what the crux of what was so difficult to describe. And we'll get into in a minute why this starts to create weirdness in how you physically interpret what that means. And we've already sort of introduced this through the lens of Copenhagen, like I said, but with probability spaces and things like this. And Max Born, the guy who was talking about figuring it, it was a footnote, I think, in one of his original papers. Just, by the way, if you want the probability of where it's going to be, you just square the wave function, you get it, because a probability has to be between 0 and 1. So if you square it, you're going to get a positive number. So it just converts it into a probability. And in a letter, Einstein wrote to Born, "God does not play dice." And this is a famous quote from Einstein, because he just was like, well, this doesn't make sense, that it's not a deterministic system, which is just going to go into one place. It just seems to be this probability space until it is made real. And Einstein really did not like this. He was like, well, there's something wrong here. It's like, if it's not determined, it can't be fundamentally probabilistic at the most fundamental level. And Niels Bohr was much more, the atom guy, he was much more just like, this is what it is. And I don't know, I haven't got any source for this, so I don't know if this is actually what he said, but he apparently replied to Einstein, "Stop telling God what to do." The implication being, this is what reality is. If it's probabilistic, if it works in whatever this, like I said, his interpretation was more just like, not necessarily probability space, but more just like, it's a bad question to ask what's going on. It's almost like a more philosophically abstract
it's fundamental,
way. And this led to a sort of, it was already part of, these guys would debate a lot. Einstein and Niels Bohr were big sort of intellectual competitors, if you like. I mean, they had a lot of respect for each other, obviously, but,
it's not like Richard Dawkins debates.
In the sciences, they were a bit slapping each other as much as they could. Everything, even when they would admit they're wrong later and like change their mind to something, one or the other, they were often like very much sparring back and forth with these sort of different interpretations. Einstein was like, well, this can't be what's going on. It can't be this probabilistic thing. There has to be what are called hidden variables. There has to be something that this photon or whatever has built into it that's going to describe how it's going to create an interference pattern.
Something we're not seeing.
There's something deeper that's going on it must be something like this, because this is crazy. Why would it be probabilistic? And we'll get on to that later and like the implications of hidden variables and where that sort of went. But essentially, nobody liked the Schrödinger. Even Schrödinger himself hated his Schrödinger equation. He was like, "Well, this is just crazy. Like this, what does this mean?
It's not helpful." Yeah.
He was very uncomfortable with this Copenhagen interpretation, which would like this idea of probability space and not being real or not making sense or not being asking the right questions until it converges on something that is real, until the probability becomes one, until it is in a place. What actually is real up to that point is very, very strange. And that's the crux of where physical interpretation comes, is asking the question, what is real up to that point? Or what is the particle real? Or is that also something that's going on? Is it something to do with observation? Is it something to do with there's hidden variables? Is there something? And we'll get onto that in a minute, but let's keep going through some of the history. So there was, in 1927, there was what's called the Fifth Solvay Conference. This is one of a line of these conferences where all these like brilliant mathematicians and physicists, basically the smartest people in the world at that point, all come together and start to discuss what the hell is going on. And this is where a lot of these sorts of debates were going on. And Bohr and Heisenberg, guy came up with a lot of maths and described a lot of this stuff. And Niels Bohr, atom guy, all that sort of thing. They were just sort of like, well, this is it, right? We figured it out. The wave function just collapses, and until that point, it's probability space, or it's a bad question to ask what that means. There seems to be something about, at least in the history, that's quite interesting, that Niels Bohr seemed to be he was either very charismatic, or he was had a particular good way of describing things or something, but he was more or less responsible for converting loads of people's minds to being very much on this train of Copenhagen.
At this conference?
Not surrounding the conference. The conference, I'm just sort of
that general time.
Yeah, this is around this general time. Like they were very much him and a lot of other scientists were kind of settled into this idea, this really strange abstract idea of this thing called superposition and things like this, or at least superposition as in the up until a point you have to describe something as being in every possible state it could be. Sort of. I think this is Schrödinger's cat time. This is a bit later on, and we'll sort of get around to. And this sort of experiment apparently came mostly from Einstein, actually, which is interesting. This was essentially a reductio ad absurdum of quantum mechanics, of the Copenhagen interpretation of quantum mechanics.
It's like a response to.
Okay, so what does this physically imply about our world? So this is where the interpretation starts to. This was the first sort of more concrete example of what Copenhagen means as a physical interpretation. And essentially, the idea is you have a box, you put a cat in it, and inside this box,
which is a cruel thing to do. Don't do that.
Yeah, don't do it. And in this box, you have a atom in a container that is radioactively decaying. And if it decays, it'll release a load of poison and kill the cat. If it doesn't decay, the poison won't be released, the mechanism won't. And essentially, this atom decaying is a quantum mechanical system. So that means there's a probability attached to whether it's going to decay or not. Now, the Copenhagen interpretation says that before you open that box, before you open up this quantum system, because it's equally real to say that the atom has decayed and hasn't decayed because it exists in some kind of probability space, or it isn't until it has actually collapsed into a thing. It's only correct to say it's in a superposition. And so that whole system within the box, because it's all attached to it's all what's called
still
coherent.
moving the framework of what you're saying is real, basically.
Well, I mean, that's sort of what quantum mechanics is.
But
it's
a thought experiment to bring this quantum effect to try and illustrate. If you were to bring it into a classical setting, this would be the implication, and
that you bracket off the whole potentiality of that happening as a superposition instead.
Yeah. So what you would say in the Copenhagen interpretation is inside that box until you've opened the box. If that's all an isolated quantum system, so everything in that box is evolving according to the Schrödinger equation, right? So which is a fundamental description which is very well tested. Well, what the atom should evolve according to the Schrödinger equation, and everything that happens in that box is a quantum system. It's an isolated quantum system. And as we know, quantum systems evolve in this sort of probabilistic way. The wave function converge on one once the superposition is collapsed. But essentially, until you interact with that quantum, until you open the box, that's all an isolated quantum system. That all exists in this wave-like space. It exists in this probability field, or it's a bad question to ask what it means to have converged before it becomes one thing. And it essentially means that you get this thing called a superposition, which is to say that the best way to describe what the cat is in is a state of both dead and alive before you decohere the systems, before you open up the box and look at whether the cat is. And obviously, once you open up the box, it converges on one. Again, talking about the probability, the wave function collapses. So everything eventually has to be that particle. Everything eventually has to collapse into something that is real. But until the quantum system is interacted with, just like those detectors at the slits, where you're interacting with the system, you're observing the system. If you don't observe the system, if you don't interact with it, again, Niels Bohr, he said it's a bad question to ask. So, or Heisenberg, it's a probability, but whatever. But the general idea is that whole quantum system, it's in that weird bit before it gets to the other side of the interference pattern, right? It's in this space of probability. It's in a superposition. The cat is in a superposition because that is part of the quantum system as much as the decaying atom is, because they're all related. They're all described by the same wave function. Until you interact with it and all your quantum wave functions or whatever become part of the same, described by the same system, the only way to describe it would be that it is a bad question to sort of ask, or that cat is in a superposition of dead and alive, because we don't know whether the atom has decayed or not, and it's a probability whether it has or not. And in the Copenhagen interpretation, that fact that it either decays or hasn't is a bad question to ask, that it has or hasn't before you observe it, before the wave function collapses.
I'm getting flashbacks.
See if like where
if
we are.
If a tree falls in a forest.
Yeah.
Well, yeah, kind of similar.
Yeah, sure.
Yeah, it's a really abstract thing to think about, and I think it's a point worth coming back to again. I think we've mentioned before, we'll probably mention again before the end, in that trying to apply our own understanding of the world to this subatomic world where this quantum that we're trying to describe with quantum theory basically almost never makes sense. Any analogies that we draw are inherently flawed, and this is why the Schrödinger's cat thought experiment is just saying, well, we're going to try and draw some sort of analogy and comparison anyway, and it's obviously really weird to a lot of people, everyone, and it should be, because it's illustrating that these quantum systems behave so differently from what we're used to. And the Copenhagen interpretation, as you mentioned, it was most popular back then. I think I'm right in saying it's still the most popular. But it's I'm personally not comfortable with it, and I don't think many people. I
don't think anyone is. I think even the people who advocate it.
I think this is probably one of the reasons why there's some contention between STEM fields and humanities. I think it's bridging that gap. It's being able to, for instance, if you're trying to do philosophy, to be a philosopher of science it's a very hard position to have, because you've got to understand this and you've got to understand philosophy, and very few people understand either isolated. To understand them both and be producing like novel ideas in that field is that must be very difficult.
It's extremely intense trying to like match all these things and then really have a grounded understanding. Like it's sort of like this complexity bottleneck almost, where these things can get so heavy, especially like with the maths and whatever of these things, and there can be so many factors and things you have to consider and different interpretations and things like this. You have to first understand, and then you've got all the your philosophical musings and frameworks that you're going to try and apply all this stuff with. I stopped doing science at GCSE. After GCSE, I think I got a B, and I just accepted that and moved on. I might have got an A, but definitely didn't deserve it if I did. But like since then, doing philosophy, I've come across very little science. But the only science I really have come into contact with is like very outdated stuff through basically learning the philosophy of science in a very roundabout way. It's that whole Kuhnian paradigm stuff we've talked about before. And it's really interesting because like learning this, it's just really nice to track the history of a development in ideas. And obviously I'm even if very quickly it gets totally mental, like, and if you're also listening and you're feeling confused, like this is honestly, it's still confusing to people who like do this for years. It's still very, very difficult.
Well done. But so I'm thinking about paradigms in the back of my mind, and like the way that Kuhn kind of likens a scientific revolution in a paradigm to a social revolution. And like the way you were talking about how certain things weren't working in terms of the explanation, and that's kind of that's analogous to. I mean, we'll talk in another podcast about exactly what Kuhn is saying.
Yeah, I have quite a lot to say about the structural revolution.
Yeah, of course. Yeah, and I know we have kind of differed in some of the interpretations of it, and but basically, analogously, he's saying that that thing when certain explanations aren't working, when the model isn't fitting the function, is basically akin to like a political system failing, and you have these revolutionaries. And I think it's a very useful way, and it's a very good way of understanding what's happening conceptually. Thinking of some of these people as revolutionaries, how the consensus isn't working, and you kind of think of them overthrowing a government. It's kind of.
I think one of the only problems with it is so much structure is retained. I mean, I've already mentioned, just going through this particular history you've gone through, things like the Maxwell equations are still very, very useful ways of describing light.
Yes,
until you get to a certain resolution, and then it starts to become
this
difficult.
is something I'm picking up on. It's like there is no date when the government gets overthrown. It's very gradual, and this isn't like. I think we've thrown many narratives back, because the one I studied was the transition from the Aristotelian to the Copernican model of the universe. That was it was that shift, and by the time we got into Newtonian physics, I'd already kind of written my essay based on that. And obviously, Kuhn only gives examples of like 3 paradigms anyway. This more interestingly highlights some of the flaws in that analysis.
Well, because I don't think it's necessarily Kuhn's analysis. I think a lot of it is the interpretation of his book, and we'll get into that, because I have as I said, I read it.
At least it shows that these things are less clear cut in terms of the development and the gradual adoption of a new paradigm.
Also, it's interesting how often we classify like an entire sort of idea on one person. Like, so I mentioned Einstein 1905 equals HF, talking about quantizing light. But that H that is critical in all of that stuff came 5 years earlier from Max Planck. And he was the first one to sort of get it. And then Einstein took that idea. So it's like, who really quantized light? Was it Einstein or was it Planck? I mean, Planck didn't really know what it meant when he had a constant, so kind of Einstein. But it's like there's so much structure that is sort of being retained, and there's such a smooth transition.
And I think it's easier to obviously think about going back in history and science, because it's kind of easier to understand. But even with like Copernicus and Galileo, like that, where did that paradigm begin and end? Is to call it one paradigm into another is, and how are you classifying that? Because you're talking about consensus. That's a very hard thing to gauge, because I guess that's how you judge what is fact at the time, the scientific consensus of the community. You had Vatican scientists, you had all these other people trying to kind of get in on the conversation as well. It's like who judges what, which I think is a very interesting element of it. But even then you have other people into that conversation, and it's just there's no point where it kind of transitions over very cleanly.
And there's still, like I said, there's still so much structure that we still use, and it works within a given resolution. That's the way I tend to put it, is in the word resolution, because that's sort of almost a visual metaphor for how it works. Is that you can use Newtonian physics, and it works if you're in like a non-inertial reference frame, as it's called, and people can look that up if they want. And it still works.
That's exactly what Kuhn says.
It's about constraints, and it's about describing something within a given number of constraints. And this has effect on emergence and things like this, which again is like all stuff I really want to talk about in the future. But
that's the thing. Reality isn't changing. The model by which we use to understand reality is changing. But the old models still work. Like you were saying about Aristotle and the feather loves the ground, that works. It's just, there is a point where you push that to its limits and it stops to work. But for the most part, that still
depending
works.
on the context, it can work.
So it's when you introduce new contexts that it kind of starts to break down. But it's like cartography based on Ptolemy's model of the universe still works. People had star maps that were pretty much accurate, but their whole understanding of where everything was situated was total bollocks. But it still works if you want to make a map of it or like plot a course on the ocean.